Okay. From the last part, we have small subtopic to be covered. So we cover that and we move on to the chapter 3. So the last part we have to discuss is coefficient of determination. Coefficient of determination. Sorry, coefficient of variation. Coefficient of variation, determination that comes up. Coefficient of variation. So now, why we need this coefficient of variation? So let me give you a simple example. Suppose there are two people. So we say A and B. So A is earning, say 100,000 a month. A is earning 100,000 a month, and B is earning 50,000 a month. Right? So that's their mean salary, like. Then on a particular month, both are getting 5,000 less than their usual. So A is getting 5,000 rupees less than his usual salary, and B is also getting 5,000 less than his usual salary. So now if that is the case, the amount less is same, but where will the impact be more? A or B will feel it more? B will feel it more. Okay, so now if you look at the value, this is 5,000, that is also 5,000. So, but why are we saying B will feel more? Because this 5,000 we are comparing with this 50,000, and this 5,000 we are comparing with this 100,000. Then okay, he will feel more. That's why we say that way, right? So when we want to compare the variation, or spread, you have to take the mean also into account. Right? You can't just compare the differences, right? The variation, only the variation part you can't compare. So if you want to compare, you have to take the mean also into account, and relatively you have to compare where the impact will be more. So this coefficient of variation is one such measure. If you want to compare the variation or spread, you have to use this coefficient of variation. Okay, so you have put the heading, so you can take down this bit underneath. If we want to compare the spread or variation, compare the spread or variation, we have to take the mean also into consideration. We need to take the mean also into consideration. First, coefficient of variation is one such measure. Coefficient of variation is one such measure. We can use to compare the spread or variation. Right. So how this is defined? So the PV, coefficient of variation. So this coefficient of variation is defined this way. Standard deviation. I am using SD for standard deviation over mean into 100. So this is how the coefficient of variation is defined. Standard deviation over mean into 100. So why this 100? Now for a data set, if you compare the standard deviation value and mean value, standard deviation will be smaller than the mean. So if you divide a smaller value by a larger value, you get a fraction as the answer. So to make that fraction a larger value, you are making it a percentage. So that's why that 100 is there. Otherwise, there is no use in this 100. Standard deviation when compared to mean, this will be smaller value. When you divide by a larger value, you get a fraction as the answer. To make that fraction a larger value, you are making it a percentage. So if we want to compare the variation of spread, we calculate the CV value, and depending on the CV value, we can say which one is having a wider spread of the variation. So CV value high means, so this coefficient of variation, we say CV value. So CV value high means the spread is more. CV value high means the spread is more, right? So CV value high means spread is CV value. High means spread is. So this is what we discussed. Take one example and finish that chapter 2. So the example says government statute. Government statistics on basic weekly wages of workers in 2 countries shows the following. Country B, X bar is 120, S standard deviation 55. Country W, X bar is 90, standard deviation is 50. So they are asking us, can we conclude that country B has a wider spread of basic weekly wages? So if you want to compare the spread of variation, we need to calculate the CV value. So what we can do is, for country B, we can calculate the CV value. For country W, we can calculate the CV value. Then by looking at the 2 CV values, we can decide which country is having a wider spread. So we'll calculate the CV value. So country B. CV value. So the formula is there. Standard deviation over mean into 100. So standard deviation, country B, standard deviation is 55. Mean is 120 into 100. So we can simplify. So we get a percentage value. So similarly, we can calculate country W CV value. Country W CV value, same formula. Standard deviation 50, mean 90 into 100. So again, we can get the value in the percentage. Right. So now we know CV value high means the spread is more. Out of the two countries, which country is having a higher CV value? We have to check. So this is country W, country B. Some 55 or that, 45 or that values. So this is 45.8. We'll go up to one decimal, properly rounded, so 45.8. So this is 55.55 or 5, properly rounded, okay. So now CV value 45, CV value 55. CV value high means the spread is more. So according to the CV value, country W is having a wider spread. But they are asking us, can we conclude country B has a wider spread? Answer is no. Why? According to the CV value, country W is having a wider spread. No, according to the CV value, country W has a wider spread of basic, weekly, weekly. According to the CV value, country W has a wider spread of basic, weekly. So how we got that from that statement? CV value high means the spread is more. So that concludes chapter 2. So we have done 2 chapters, measures of central tendency, chapter 1, measures of dispersion, chapter 2, and I will chapter 3. Okay. Correlation and regression analysis. So that is chapter 3. correlation and regression. So that's a very easy chapter. So now, what is this correlation? What is this regression? Now, consider these pairs of variables. So now if you take these pairs of variables, amount of fertilizer used and yield, we feel that there can be some sort of relationship. Price and profit, we feel that there can be some sort of relationship. Age and hearing ability, price and demand. So we feel that there can be some sort of relationship. So in statistics, by feeling something you can't prove. For anything, you need a measure, you need a value to show that it is there. So this correlation is a measure used to identify whether there is a relationship between the variables and the concern. So correlation is a measure used to identify whether there is a relationship. Right. So now suppose you are given a data set, you have used the correlation, and correlation tells you, okay, there is a relationship. Then the next question comes in is, then what that relationship is. That relationship, what that relationship is answered through regression. So that's how the entire chapter goes in. Using correlation, you check whether there is a relationship. If the correlation tells you that there is a relationship, using regression, you identify what that relationship is. Okay, right. So after the heading, we'll just write down the stuff. Correlation and regression analysis. Correlation and regression. So underneath we can put down this way. Consider the following pairs of variables. Consider the following pairs of variables. Consider the following pairs of variables. Amount of fertilizer. We'll put it in bullet points. First bullet point. Amount of fertilizer used and yield. Second bullet point. Price and profit. Third one. Age and hearing ability. Age and hearing ability. Age and hearing ability. Fourth one. Price and demand. Price and demand. Amount of fertilizer used and yield. Price and profit. Age and hearing ability. Price and demand. When we look at these variables, continue. When we look at these variables, we feel that there can be some sort of relationship. We feel that there can be some sort of relationship. We feel that there can be some sort of relationship. Feel that there can be some sort of relationship. In statistics, we need a measure in statistics. We need a measure to prove. We need a measure to prove. So correlation is a measure. So correlation is a measure used to identify. Correlation is the measure used to identify whether there is a relationship. Correlation is a measure used to identify whether there is a relationship between the variables under concern, between the variables under concern, between the variables under concern. If the correlation tells us that, if the correlation tells us that there is a relationship, if the correlation tells us that there is a relationship, the next question is, what is the relationship, or what the relationship is? What the relationship is. This question is answered through what the relationship is. This question is answered through regression. This question is answered through regression. Right. This question is answered through regression. What the relationship is, this question is answered through regression. Okay. Right. So now, again, look at these ones. Amount of fertilizer used and yield. So when we look at this one, okay, there should be a relationship. Apart from that, we feel that like this yield depends on the amount of fertilizer used. And price and profit. So we feel that, okay, the profit may depend on price. Hearing ability depends on age. So now if yield depends on amount of fertilizer used, yield is the dependent variable. So if yield is the dependent variable, automatically this becomes the independent variable. Yeah, profit depends on price. Profit is the dependent variable. Price becomes the independent variable. Here, hearing ability depends on age. So hearing ability is dependent, and age becomes independent. Last one, price and demand. You can argue either way. You can argue demand depends on price. If you want, you can argue the other way around as well. Price depends on demand. So whatever the way you argue, there will be a dependent variable, there will be an independent variable according to your need. You can argue that one. Right. So now everywhere we have a dependent variable and an independent variable. So in this section, we don't call it as dependent and independent variable. So in place of dependent variable, we use the term response variable. Same thing, but we don't use it, right? Dependent variable, we call as response variable. Independent variable, we call it as explanatory variable or influencing variable or predictor variable. Same thing, but we don't use those terms. Instead, we use this or one. Okay. In this section, dependent variable is called the response variable. Dependent variable is called the response variable. While independent variable is called explanatory variable or influencing variable or predictor variable. Explanatory, influencing or predictor variable. Now, usually first we collect data. So after collecting data, we have to check whether there is any sort of relationship, right? For that, we use the scatter diagram. Now suppose you are given a data set, right? Some X values, some Y values, maybe price and profit. Don't know whatever it is, right? Dependent variable, independent variable, dependent variable, response, predictor. So now when you are given a data set, you can draw the scatter diagram. How do we draw the scatter diagram? Along the x-axis, we take the predictor variable values. Along the y-axis, you take the response variable values. Then you mark the point. So here 255, 255, you mark the point. 358, 358, you mark the point. The 549, 549. So likewise, you mark all the points and leave it. So you mark all the points and just leave it. What you get is the scatter diagram. So now we get this is the scatter diagram. So now after drawing the scatter diagram, from the structure, we can identify whether there is any possibility of a relationship. So these are not proofs. You can't use diagrams for proofs, right? Diagrams are there just to help us. So we draw the diagram and we just see whether there is a possibility of a relationship. So if you see any possibility of a relationship, then you have to do the calculation and show, okay, there is a relationship, right? You can't give it as a proof, right? Okay, so now if you draw the scatter diagram, right? When you draw the scatter diagram, when you have a data set, now you know how to draw the scatter diagram. Along the x-axis, you take the predictor variable values. Along the y-axis, you take the response variable value. Just mark the points and leave it. What you get is the scatter diagram, right? So now after drawing the scatter diagram, these are some of the possibilities. You may get a structure like this. Or maybe, I'm not saying these are the only structures. No, these are some of the structures. You may get a structure like this, or maybe you may get a structure like that, or maybe something like this, or maybe something like that. Now, by looking at this one, how to identify what sort of relationship is there, right? So before going into that, first we'll recall the general equation of a straight line. The general equation of a straight line is y equals mx plus c. M is the slope or gradient. Slope or gradient. C is the intercept where it cuts the y-axis. Right. Now, if you have a straight line, slanted towards the right, if you have a straight line slanted towards the right like this, what can you say about the slope of that line? We can't say what the value is. What is the slope is, we can't say, but we can say that has a positive slope. So any line of this inclination will be slope. Positive. Now, if you have a line slanted towards the left like this, then it has a negative slope. M is less than 0. Right. So general equation of a straight line is y equals mx plus c. If you have a line slanted towards the right, any of this form, then we can say it has a positive slope. It has a positive slope. If you have a line slanted towards this way, then negative slope. Now suppose you are given a data set and you have drawn the structure and you got this scatter diagram. Now, if you get this scatter diagram, then you can think of an imaginary line like this. So the points are evenly distributed along this line. So points are closer to a straight line. That straight line is slanted towards the right. See how we build. Points are closer to a straight line. Straight line is slanted towards the right. If you have a line slanted towards the right, it has a positive slope. So this structure shows a positive linear straight line, so linear relationship. Now that one, points are closer to a straight line is slanted towards the left, then it has a negative slope. So that shows negative linear relationship. Then if you come to this one, first we have to see should have some kind of nice structure. So here we have a structure. So there is a shape, so there is a relationship. But that is not a straight line. If it is a straight line, we say linear. This is not a straight line, so this is non-linear curve type. So here you can have any curve type. You can have a maximum type like this, or minimum type like this, or maybe exponential increasing, or maybe exponential decreasing. Any type of curve is possible here. So non-linear relationship. If you get something like that, the last structure, we can't see anything, points are scattered everywhere, so no relationship. So if you are given a data set, we can draw the scatter diagram. From the scatter diagram, we can identify whether there is a possibility of a relationship. Right? You get this type of structure, positive linear relationship is possible. Negative linear relationship is possible. Non-linear relationship is possible. And this last one, no relationship, because there's nothing everywhere scattered. So no relationship. So now we'll write down whatever the start be. When we are given a data set, next parameter write down. When we are given a data set, we can draw the scatter diagram. We can draw the scatter diagram. From the scatter diagram, we can identify. Whether there is a possibility of a relationship. Stop, continue. When we draw the scatter diagram, for a given data set, the following possibilities are there. Right? So those are the four possibilities. Positive linear relationship, negative linear relationship, non-linear relationship, no relationship. ඔයගොල්ලන්ට උගන්වන්න. පොඩි ළමයිට උගන්වනකොට හරි අමාරුයි ඒගොල්ලෝ කතා කරනවා. හරිම ඩිස්ටර්බ්. ඒකට මගේ ෆ්ලෝ එක යන්නේ නැහැ. ඒ අමාරුයි. ඒකට මේවත් ඉන්නකොට අර ඔයගොල්ලෝ තුනන් දෙන්න බලක් ඉන්නවා. So it's very easy for me. මම කියන්නේ ඔයගොල්ලෝ වයස කියලා නෙවෙයි. So that other part also, if you want, you can note down somewhere. If you have a line slanted towards the right, positive slope, slanted towards the left, negative slope. So if you want, you can make a note of it on sides. So that's fine. So here you can have any kind of curve, right? So only one type I have shown. You can have any type of any kind of curve is possible, right? Non-linear, right? Without any straight line, you can have any kind of curve. So now using these structures, we can identify whether there is in some sort of relationship. So if you get any of these structures, okay, then we check whether there is really a relationship. So for that, we need a measure. So the measure we use to get the correlationship is correlation, but first we'll discuss Pearson score because there are two correlations. Another one is there Spearman correlation and Pearson's correlation. So Spearman correlation we won't be talking here because that is a non-parametric test, non-parametric one. So here we will be discussing Pearson's correlation. So this Pearson is a name of the person who invented this correlation, right? Pearson's correlation part. Next up. Pearson's correlation part. Pearson's correlation coefficient. Right. So what are the other names we use for the same correlation? So you can call it as Pearson's correlation, or we can call this as Carl Pearson's correlation. Carl Pearson's correlation. That is his full name, Carl Pearson. Or else it's simply given as correlation. correlation coefficient. That also means the same thing, right? So Pearson's correlation, Carl Pearson's correlation, or simply correlation means the same thing, right? Pearson's correlation, Carl Pearson's correlation, or correlation coefficient, right? So how do we denote this Pearson's correlation? So this Pearson's correlation is denoted by simple R. Pearson's correlation is denoted by simple R. And I told you there is another one called Spearman correlation. For that we use capital R, but we won't be talking about that, right? So here we will be talking about Pearson's correlation, simple R. Okay. So now how this is defined. So there are two formula for this. So this is the original version of this Pearson's correlation. R is defined as Sxy. So this x and y should go as a subscript over square root of Sxx into Syy. None of these terms are known, so each term is defined separately. So we have to calculate all these three pieces and then plug in here, get the value. So this is the original version of the Pearson's correlation. And there is another derived version also. First we'll take down, after that we can do. So carefully have a look at the formula and write down. So here x minus x bar, y minus y bar. This is x minus x bar whole in square. Y minus y bar whole in square. So this x bar, y bar, what we talked about in central tendency. Sample mean. So that's the original version of the formula. So the derived version, or sometimes we call this as the simplified version. So when you say simplified version, application-wise simplified version, right? Otherwise, if you look at the formula is larger than the previous one, right? So application-wise, when the formula is large, application-wise easy. When the formula is compact, application-wise it's hard, right? So this is the derived formula. So the first example we'll do using the original version as well as the derived version. After that, you can decide which one is easy, then you can use whatever you feel easy. So this is the derived version. So here we have a n sigma xy minus sigma x, sigma y, square root. Two pieces are here. N sigma x squared minus sigma x whole thing squared. Here nothing is there, that means it is multiplication, right? Here multiplication. N sigma y squared minus sigma y whole thing. Here we have this n. N means number of pairs of data. How many pairs you have? That is n. N is number of pairs. Right. So now we'll take an example using the first as well as the second. First example, which says find the Pearson's correlation coefficient of the given variable using the original formula and the derived formula. So when you take down this data set, make sure you leave maximum space on the right side so you can work out on the same. So leave maximum space to that. That is profit. So first we'll use the original version. So original version formula is R equals Sxy square root of Sxx into Syy. So this Sxy is sigma x minus x bar y minus y bar. Sxx is sigma x minus x bar whole square. Syy is sigma y minus y bar whole square. Right. So we need to evaluate these pieces. So to evaluate these pieces, we need x bar and y bar. Right. So we need formula for that. So x bar is sigma x over n. Y bar is sigma y over n. So first we need to get this sigma x and sigma y. So here we are given in terms of real names. So we have to identify which one is x and which one is y. X is the predictor variable, y is the response variable. So generally look at these two and identify which one depends on the other. Is it price depends on profit or is it profit depends on price? So easiest way is profit depends on price. So this is your Y. This is your X. So we have identified. I generally think of and get okay, this one depends on that. Y, X. So we need the sum, right? So if we add, we get sigma X. 5, 10, 17, 27. So we need sigma Y. Here we have a 0.5, 5, 3, 4, 11, 17, 1, 2, 3, 4, 47.5. So we have the values. Sigma X 27, N is 5. So we can simplify. Okay, I don't have space, so I'm writing inside. So this is 5.4 X bar. So here 47.5 over 5. How many pieces? Right, 5 pieces. So this is 9 point. So X bar, Y bar calculated. Now next we have to decide what are the columns we have to develop. Right. Already we have X and Y. We need to get all these summed. Whatever the sigmas needed, the corresponding column we have to develop. So we have X, we have Y. So what are the other columns we have to develop? So we have to develop, right? X minus X bar needed, X minus X bar we need to develop. Y minus Y bar we need to develop. If we have those two, then this product we can develop. X minus X bar, whole things, X minus X bar, Y minus Y bar we can develop. Then we need X minus X bar squared, that also can be developed. X minus X bar squared. And Y minus Y bar squared. So all together, 5 columns we have to develop. X minus X bar, Y minus Y bar, in this product, this square and that square. So 5 columns we have to develop. X bar means the value we found. Y bar means the value. Excellent. 579. Okay. this is your XY, this is your SXX, and this is your SYY. Now we have the formula. First X, X, Y, square root of SXX into SYY. So we substitute the values. This is 38.5. SXX is 41.2. And that is 37. Now it's just a matter of simplification. So if you simplify, you get 0.986. 0.986. So we give 3 decimal place, right? 3 decimal place properly rounded off. 3 decimal place. Answer. So we are getting a value of our R, we are getting a value. So that's the measurement. So always when we give the answer, we give up to 3 decimal places properly rounded. So if you are using the original version, that's how you have to do, right? So we have to calculate X bar, we have to calculate Y bar, and then this column, this column. So nothing to memorize. By looking at the formula, you decide what are the columns you have to develop. Whatever the sigmas needed, the corresponding column should be developed. So now the second formula, the second formula is R equals N sigma xy minus sigma x sigma y over square root of 2 pieces n sigma x squared minus sigma x whole squared into n sigma y squared minus sigma y whole squared. Right. So we have 2 columns, right? So the 2 columns we have x and y, x, y we have. Now, if we are going to use this formula, what are the other columns we need? Right, whatever the sigma needed, the corresponding column, sigma xy needed, so we need the xy column. Sigma x needed, x is already there. Sigma y needed, y is already there. Sigma x squared needed, we don't have, so we have to develop x squared. Sigma x whole thing squared, x needed, x is there. Y squared, sigma y squared, we don't have, so we have to develop y squared. Sigma y whole thing squared, y needed, y is there. So just 3 columns we have to develop. X, y column, x squared column, y squared column. And we need all these totals. Y needed. X squared needed. Y squared. So even we don't need the calculator. I will have simple values. 2 into 6, 12, 21, 50, 77, 135. X squared. So 2 squared, 4, 3 squared, 9, 5 squared, 25, 7 squared, 49, 10 squared, 100. Here, 6 squared, 36, 7 squared, 49, 10 squared, 100, 11 squared, 121. And only we need the cal for this 13.5 square. So then we need all these two. Now we can substitute the values. And how many pairs? We got 5 pairs, 5 sigma x y, so 295. Sigma x 27. Sigma y, that is 47.5 over square root, don't forget the square root, 2 pieces, right? 10, so that is 5 sigma x squared 187, 27 squared, done for that. Next again 5 sigma y squared 488.25 minus 47.5. So if you simplify, you get that. Right. So when you are calculating, if you are using your calculator, try to get that once. Right. So then you don't make any rounding of errors. Right. Otherwise, if you calculate this separately multiply, then you take the square root, you go up to 2 decimals, then you divide this, then okay, so you will get a different answer. Because the square root will be a lengthy answer. So if you are part by part doing it, right, so keep the solution in the calculator itself and use that value to calculate. If you're using the calculator on shortcut, that's how it works. Top part, you have several components, so you start with the bracket. So this is the top part, 5 into 295 minus 27 into 47 plus bracket. Top part, division. Then you have a square root. Inside the square root, you have two pieces. So here we have a. So here you have starting bracket. Here you have a starting bracket. Here you have another bracket. So that is to put all the things written here coming into the square root. And then here this is one part. This is the other part. In between multiplication. After finishing everything, you put the equal sign. So both ways we have done. So now you can think of whatever the one you feel easy and you can go for that. So the issue is like this now. See, when if you go for this second one method, if the x and y values are large values, then when calculating these squares and the product, you have to deal with large numbers. So that is the issue with this method. And the previous one, if the x bar, y bar are decimals, right? In the previous one, if x bar, y bars are decimal, then you have to deal with decimal numbers. So that's the only issue. But anyway, the second one, this method is easy, though we use the large values, it's easy, right? So it doesn't matter if you feel the first one is easy, you can use no. So anyway, you'll be getting that. So now we'll take another one. Take another one. So you use whatever the one you feel easy. Okay. Price and demand. Identify whether there is an association. This is another way of asking is whether there is a relationship or whether there is an association between the given variables. Using the formula you think is. So as in the previous case, leave space on the right side for you to develop the requirement. minus 9.4 minus 0.91. So first example, we got a positive value. Second example, we are getting a negative value. Now, whenever we calculate some value or measurement, we should be able to explain what does that mean, right? So now we have the value minus 0.921. So how to interpret this? So now we know how to calculate, and you have decided which formula is easy for you. So hereafter you can use that formula and do the calculation. So now after calculating the value, how to interpret this value? Now to interpret, we have a scale, right? We have a scale. So rather than memorizing those values, if you know how to develop the scale, then it's easy. You don't have to memorize the values. So we'll see how to develop the scale, right? So we can take that. To interpret the Pearson's correlation, interpret the Pearson's correlation, we have a scale. We have a scale. Okay. The next line, I write down this way. According to the way Pearson's correlation is defined, according to the way Pearson's correlation is defined, always it will lie, between -1 and +1, -1 and +1 inclusive, between -1 and +1 inclusive. So that means what they say, -1 +1. Always this R lie between these two. So less than or equal to R, less than or equal to R. Because equal is also inclusive. 1 is possible, -1 is also possible. So now, how do we develop this scale? Now we said, okay, so this is given. Now see, when you calculate, if you get a value above +1, or if you get a value below -1, that means something wrong in the calculation, right? If you get a value above +1, or if you get a value below -1, something wrong in the calculation. So in that case, you have to recheck, right? So now, how do we develop the scale? Now here it says -1 to +1 possible, right? So what we do is, so we do like this. We take all the values from -1 to +1. We take all the values from -1 to +1. 1 to +1. We take all the values. And then we divide this into 2 equal parts. So this length, we divide into 2 equal parts. So if we divide into 2 equal parts, this will be 0. Right? Then each sub part we divide into 5 equal pieces. 5 equal pieces. This side also we do the same thing. We divide into 5 equal pieces. So this will be plus 0.20. This will be plus 0.40, plus 0.60, plus 0.80. This side you get, this will be minus 0.20, minus 0.40, minus 0.60, minus 0.80. Right, so you take the full length, minus 1 to minus 1 to plus 1, divide into 2, so middle value will be 0, each apart, you divide into 5 equal. Right. So now you get something like this. Minus 1 to plus 1, divided into 2, 5 equal. Okay, right. So now, two examples we discussed. One example is positive one, plus, other one is minus. So if it falls in this region, positive relationship. If it falls in this region, negative relationship. Okay, if this is positive, this is negative, then why we need these segments? So these segments are there to identify what is the strength of the relationship. Is it okay positive, but is it a strong one, or is it a weak one, or is it a moderate one, or very strong? What type? So that is given by these segments. Okay, so we'll see what are the segments, which segment represent what case. So you can take the full length, divide into 2, 5 equal solution. After that, we see. So this scale is developed up to 2 decimal place, 2 decimal. So positive relationship, negative relationship. So suppose now you are given a data set. You are given a data set and you have developed that, you have calculated the R value. So when you calculate the R value, we'll say you are getting exactly plus 1. So plus 1 means positive relationship. So in the structure, we have seen positive relationship means something like this. Slanted to the right and the points are evenly distributed along this line. So that is positive relationship. But for a data set where this R equals plus 1, the points are not closer to the straight line. Straight line is slanted to the right, but the points are not closer to the straight line. The points are on the line. R equals 1 means the points are on the line. So you can't have anything better than that. So that's a perfect fit, right? That's a perfect fit. So if your R value is 1, exactly 1, then it is perfect positive linear relationship. R equals 1 means perfect positive relationship. So similarly, you can have R equals -1 also. You can have R equals -1 also. So if your R equals -1, then it is perfect negative relationship. So the structure is symmetric, right? Perfect positive. Here, perfect negative, right? Okay. So R equals 1. R equals 1 means here. So 1 we consider separately. So R equals 1 means perfect positive linear relationship. We have to just remember the term. So this is perfect positive linear. I use PLR to say positive linear relationship. So similarly, if you have R equals -1, R equals -1, then it is perfect negative linear relationship. So I'm using NLR for negative linear relationship. Perfect positively PLR, positive linear relationship. Perfect negative linear relationship. Okay. So now, when R equals 1, the points are on the line. So what happens when R move from 1, R move towards 0, what happens? So the strength little by little reduces. So the structure also, R equals 1 means all the points are on the line. So when R moves towards 0 this way, the structure becomes larger and larger, right? It gets away from the line. Okay, the relationship. So this side also, if you take R equals -1 means you will get a structure where all the points are on the line slanted towards the left. Then when R moves towards this way to 0, the structure also little by little gets like that. Okay, so the strength reduces. So R equals 1 is perfect. So next level. Now we are going up to 2 decimal place, 1 given for this category. So next category is this. From 0.8 up to 0.99, because 1 given for this category, we are going up to 2 decimal place. So the next point here would be 0.99. So from 0.8 up to 0.99. Border to inner, right? Border to inner. So this region, perfect. This is very, very strong. This region, 0.8 to 0.99, very strong. Very strong. Positive linear relationship PLR. So similarly, this side also from 0.99, minus 0.99 to minus 0.8. Border to inner to border. So this is very strong. Negative linear relationship in area. Negative. 0.99 to 0.8. Border, inner to border. The next level. 0.8 given for this category. The next level. 0.6 to 0.59. 0.6 to 0.59. So that is, this is very strong. Little by little the strength reduces. So this is just strong. Strong positive linear relationship, 0.6 to 0.79. So similarly, the other side, minus 0.79 to minus 0.6. Strong negative linear relationship. Next one, 0.6 given for this category. So 0.4 to 0.6, 0.59. 0.4 to 0.59. So that is, this is strong, little by little reduces. This is moderate. Moderate. Positive linear relationship. So here, next one, from 0.59 up to 0.4 minus. This is moderate. Moderate negative linear relationship. So 0.4 given for this category. So next level from 0.2 to 0.39, 0.2 to 0.39, 0.2 to 0.39. So the strength further, this is moderate, this is weak. Weak positive linear relationship. So here 0.39 to 0.2 minus 0.2. Negative linear relationship. Right. So now here in all these cases it goes like border to inner, border to inner, border to inner, border to inner. But when it comes to zero, zero is considered separately. Zero is considered separately. Zero is considered. So here it will be inner to inner. So that's how it goes at this level. Here is inner to inner. Mark 0.1, 0.01 to 0.19, 0.01 to 0.19. 0.01 to 0.19. So if this is weak, that is very weak. Is very weak. Very weak positive linear relationship. So here also it is the same. My 0.19 minus 0.19 to minus 0.01. Very weak. Very weak. Negative linear. So zero we consider separately. So zero means no, you can't say no relationship, it is no linear relationship. So zero means no linear relationship. No linear relationship. Zero means no linear. So how the values go here? Zero separately. 0.01 to 0.19, 0.2 to 0.39, 0.4 to 0.59, 0.6 to 0.79, 0.8 to 0.99, one separately. Other side also doing border to inner, border to inner. So now, after calculating, say the first value we got is 0.98. So we got R equals 0.986. So the scale is developed up to 2 decimal place, but we have calculated up to 3 decimal place. So we approximate this to 2 decimal place. So if you approximate to 2 decimal place, 0.99. Now you have to see in what region this value falls in. So this 99, not 1, is here. So what is the relation? Very strong. Positive linear. Very simple, right? So if you know the scale, it's not. So the other one we got is R equals minus 0.921. So if you convert to 2 decimal place, 0.92. What region? So it falls here. Strong, negatively. Very strong, negatively. So now we take some examples and see how to interpret. Okay. So if you don't know how to develop, then you have to memorize all the values, right? 1.9. Right? So rather than memorizing, if you know how to develop, it's easy. Interpret, we'll take some example. Interpret the following correlation coefficient using the scale. Interpret the following correlation coefficients using the scale. Right. So this is the same value we calculated. R value between price and profit. Point plus 0.986. So what we do? First, we transfer this to 2 decimal place. So plus 0.99. Now in the scale, we check in what region this value is. So this is in the last level, very strong level. So how do we write? It shows that there is a very strong positive linear relationship between the two variables given, price and profit. Price and profit. It shows that there is a very strong positive linear relationship between price and profit. Are between price and demand. The same thing what we have calculated. R value between price and demand minus 921. Value between price and so we approximate to 2 decimal place, so it is 92. Now we see in what region it falls. It shows that there is a very strong negative linear relationship between price and demand. Same way you write, plugging in the corresponding values. Shows that there is a very strong positive linear relationship between price and demand. The next one. R value between age and hearing ability, right? R between age and hearing ability. Minus 0.760. Minus 0.760. So if you approximate this, then you get minus 0.76. So this falls in the strong negative region. So it shows that there is a strong negative linear relationship between age and hearing ability. It shows that there is a strong negative linear relationship between age and hearing ability. Hearing ability. The last one. R value between education and salary. R value between education and salary. Plus 0.592. Plus 0.592. Plus 0.59. So if you approximate to 2 decimal place, it is 59. So what is the relationship? Moderate. So it shows that there is a moderate, not strong, very strong, not strong, moderate, right? So it shows that there is a moderate positive linear relationship between education and salary. So after calculating the R value, we can identify what sort of relationship is there. So to interpret, we use the scale we developed. So finally, what else we can do with the correlation, right? If you know the correlation, what else we can do? So with the correlation, if we know the R value, then easily we can calculate 100 R squared. So this 100 R squared is known as the coefficient of determination. 100 R squared is known as the coefficient of determination. So this coefficient of determination tells us what percentage, now you have a dependent variable, you have an independent variable. So how much percentage the dependent variable depends on the given predictor variable. Right now, say price times profit. Profit, how many percent profit depends on price. Right, that is given by this 100 R square. Okay, so next line we write down that 100 R squared 100 R squared is known as the coefficient of determination. 100 R squared is known as the coefficient of determination. 100 R squared is known as the coefficient of determination. Coefficient of determination. Which gives us the percentage dependency, which gives us the percentage dependency of the response variable, percentage dependency of the response variable, in the explanatory variable. Percentage dependency of the response variable in the explanatory variable. How many percentage? The dependent variable depends on the given predictor. Calculate the coefficient of example. Calculate the coefficient of determination. Calculate the coefficient of determination and interpret coefficient of determination of the following. Calculate the coefficient of determination of the following and interpret. R value between price and profit plus 986. 98. So since this value is known, we can easily calculate the 100 R squared value. 100 R squared. So 100 into plus 0.986. Now for this one, you use all the 3 digits. And final answer, you go up to 1 decimal place properly wrong. 100 into 0.986 square. That's right. 97. Right, 7.1. 97.2. We'll go up to 1 decimal. So 97.2. So now what can we say with this 97.2? So the idea is given. So idea is given like this is the percentage dependency. Now if you take price and profit, which one depends on the other? Profit depends on price. So how many percentage profit depends? 97.2% on price. So that's the idea. That is not the interpretation. So the idea will write. So idea is profit depends 97.2% on price. So the idea is that. So how do we interpret this? So we have the idea. So how to interpret? Interpretation. So we get the idea. So idea you don't have to actually write. So for your reference, I have written. So this is there in our mind. So how do we write? Now see, we got this value through these values, right? So now see, this is the data set we had to collect that value 986. So now we are saying profit depends 97.2% on price. Now here in the profit figures, there is a variation, right? There is a variation. Why there is a variation? There is a variation because there is a variation in price. Further, we said profit depends 97% on price. So now we can say combining both 97.2% of the variation in profit can be explained through the variation in price. So that's the interpretation, right? So this one depends 97% on this. There is a variation here. Why there is a variation in the profit? There is a variation in the profit because there is a variation in price. So combining both, you can say 97.2% of the variation in profit can be explained through the variation in price. So that's the interpretation. So that is what we have to write if they ask to interpret. So interpretation would be first the value comes in 97.2% of the variation in profit can be explained through the variation in, so that is the 97.2% of the variation in price can be explained through the variation. Okay. So when you are given R value, we can calculate 100 R square. We can get the idea in our mind, then put the interpretation in this format. So just the format, if you take just two things you have to change, right? Here, the value according to your calculation. Predictor, the response variable name, and here predictor variable name. That's all you have to change, right? According to the problem. Those are the three things you have to change in this format. Value, response variable, predictor variable. Other ones are static. So I hope you can do that. So saying that, I'll give you two more examples. So you can try on the board. Those are the other values. Same question. This one we have done. So these three, especially do when you have. The same thing what we did as previous for the previous one, same values. Calculate the coefficient and coefficient of determination and interpret. Price and demand, age and theory, ability, education and salary. So even if your R value is negative, when you calculate 100 R squared, it becomes positive, right? Because with the minus you square, so that becomes positive. Yeah, you calculate for this. 100 into minus 0.921. Yeah, so this becomes positive. So in this case, you can argue either way. So we'll take demand as the response and price as the prediction. Here, hearing ability depends on age. Salary depends on salary depends on education. The data. So that's all we have for correlation. So next we have to discuss regression. So I think we better discuss regression.